Detailed investigation is much beyond that. Now we have very different questions. And that's the one the retrofitting will ask, not the one that we just did. That's too simple. It won't work. So now we are looking at more difficult questions. The first one is, what is the actual deflection at a certain load? The deflection that you calculate previously is based on certain formulas, I crack, and then rules. Go I crack less than this one, go this one. Effective moment of inertia based on certain things, but that's not reality. That's just an estimate for design check purposes. Then, what is the load corresponding to certain deflection control? So let's say if we want to have a certain deflection, what will be the load that will be corresponding to that particular deflection? Once again, this is not a linear relation anymore, so you can't calculate that, and the ACI code won't help you there. What is the maximum deflection before failure? What will happen when it reaches maximum moment capacity? When and where it will crack? What will be the stresses and strains in concrete and steel at a given load? This is very important question which cannot be answered by the strength design procedures, because strength design procedure is based on the failure criteria of 0.003 strain. What is the actual stress, actual strain at a given loading? We don't know, because everything is done on factored things, right? So this question cannot be answered. Then what will be the stresses and strain in concrete at a given deflection? Reverse of loading. But once again, load and deflection are not linearly connected anymore. And then what ductility does it have? So, and many more. So there are so many questions that you can ask a real structure that won't be answered by the code procedures, either design procedures or the code investigate procedures. That means now we have to go a step further into the details. What is that detail? So these are some of the limitations of the strength-based design. The cross-sections are capable of resisting certain value of loads based on certain criteria. That's the first thing, which will never ever reach. That criteria of 0.003 strain and yielding will never ever reach in any case. So that's a very artificial point on the design with no relevance to reality. So that's the first one. No information available or determined for actual loads because they're affected already. Then actions are obtained from linear analysis, design is factored, and so on. Strength is, it provides no information control on the level of deformation and so on. So there are some of the limitations. Then let's go into the detail. So if we want to do the true investigation, we have two ways. First is put the beam, test it, find out what's really happening. Second is to do a more detailed, refined numerical analysis. So if you look at this one, so this is a class project that we did, one of the class that they did the testing to answer those questions. So I put them the same question that you could do a testing and find out what happened to this beam, find out where the crack was, and then what is the total deflection, and correlate through the simulation with that. So first crack, so happy to see that. And then we continue to monitor and map the cracks. Obviously, many students do that in their classes. So you can see that it is answering now ultimate load capacity, cracking core load capacity, deflection limit, actual deflection is all being measured. So that means there's no ambiguity about the response. But the problem is we broke the beam that we were trying to find. So there's nothing left of the beam. So what's the point? You can't do this on every structure. So which means that you need, and you got the response, strains and nonlinear plots and everything that you wanted, that you were looking for, you got it. But you broke the beam in the process. So which means that now we need a better way to do that. And that is the simulation. Detailed simulation going beyond the capacity design procedures. So of course now we have a beam here, and we have seen that the load deflection curve is not linear. It's going to go like that. We've observed from the, so this is actually a plot of that same beam, actual plot, it goes up and goes down, we all know that. And then the right hand side is the theoretical capacity diagrams for a beam or a column. And you can see here that this one is the one which is with phi factors, this is without phi factors, and there's a big gap between them. So that means there's a huge gap in between the actual theoretical computed capacity and what the code will allow us to use. And that means in between is a gray area. What's really happening? Is it failed? Is it there? Because if you test it, you will find the blue curve. But the codes will ask you to design for the red curve. So in between, what's happening? We have no information because that is not explored. And then, so a point is inside, we call it safe. Point is here. So this point is safe according to the code. This point is safe according to the actual capacity, but not safe according to the code. And that point, according to the capacity and code, is unsafe. What does it mean, unsafe? What happened here? Is the beam gone? We have seen that beam doesn't go away like that. It's still there for a long time. Even after everything is gone, the beam is still there. We actually couldn't break it. We had to stop the testing because the deflection was too much, but actually the beam was still there. So what does it really mean to have a failure? Okay? So that's what we are going to now look at and see how we can study those effects beyond the strength design.